All right, so we're going to start out with the mixture problems are first. What it says at the top, these are all types of problems that deal with weighted averages. So it's a method for finding the mean or the average of a set of numbers in which some elements of the set carry more importance or weight than others. So a common example of a weighted average that applies to all of you would be your GPA. Higher grades have a higher weight on your GPA than lower grades. And then many real-world problems involving mixtures work in distance. Distance we're working on Monday. And interest can be solved by using rational equations. So examples 1 and 2 are both mixture problems. And reading the problems, they might seem familiar, the wording, you might remember solving problems like this. If not, it's fine. I'm going to show you how to solve it. So it says Jimmy adds 65% fruit juice solution to 15 milliliters of a drink that is 10% fruit juice. How much of the 65% fruit juice solution must be added to create a fruit punch that is 35% fruit juice? So I'm going to show you how to set these up. Ultimately, I'm just going to highlight here what we're trying to find. We're trying to find how much of the 65 fruit juice solution must be added. So the amount of the 65% fruit juice solution. So I would recommend, like I said, there's multiple ways to set these up. I would recommend setting these up using a chart. So kind of like a 3x3 chart is what I'm going to create here. So I'll explain what everything in the chart represents as well. So what we're going to have is we have two different concentrations of fruit juice that are being mixed together to create this fruit punch. So I'm just going to say, however you want to label it is up to you. I'm just going to say juice 1 and then juice 2, and then the bottom would be the mixture, and that's the fruit punch. And then, so that's what the rows would represent. So the first row I'm letting be one of the fruit juices, and then the second row would be the other one. The bottom row would represent the mixture or the fruit punch. Now for the 3 columns, the first column would be the amount of the solution. So the amount of solution. The middle column is going to be the percent of juice that's in the solution. So that's giving us the 65%, the 10%. We want the fruit punch to be 35% fruit juice. And then the final column is going to represent the amount of the juice. Okay, so there's the amount of solution. There's a certain percent of juice in the solution. The last column would be the actual amount of the juice. So then how to fill this in? I'm just going to read back through the problem. It says Jimmy adds a 65% fruit juice solution. So I'm going to say juice 1 is the 65% fruit juice solution. So in that percent juice column for juice 1, I'm going to put 65%, but I'm going to write it as a number, not as a percent, so 0.65. And then that is being added to 15 milliliters of a drink that is 10% fruit juice. So juice 2 is going to be the 10% fruit juice solution, so I'm going to put 0.10 or just 0.1, so 10% in the percent juice column. And I know the amount I have of that is 15 milliliters, so I'm going to put 15 in that first column for juice 2. Okay, I don't know how much I have of the first juice, so that's going to be my variable. I'm going to call that x. So it says how much of the 65% fruit juice solution must be added to create a fruit punch that is 35% fruit juice. So I know the mixture, the fruit punch, the percent of the juice should be 35%, so 0.35. And with that information, I'm able to fill in all of the blank spots I have in this chart. Okay, so how to fill in this amount? First of all, the amount of the solution for the punch. If juice 1 and juice 2, if these are being added together, they're being mixed to create this, then the amount of each must be added to get the amount of the mixture. So this amount must be x plus 15. I'm adding x milliliters plus 15 milliliters, so that's just the amount. And then, if I have the amount of each solution, I have the percent of juice that's in each solution. To find the amount of juice, I multiply these two columns across for each to get a value or an expression here. So for example, for juice 1, the amount of juice would be 0.65 times x. So I would have 0.65x. So the percent of the juice multiplied by the amount of the solution as a whole. So then for juice 2, I would have 0.1 times 15. And since they're both numbers, I can actually just calculate that. But it would be 1.5. If you want to write in your notes that you'd multiply those just so you know where the 1.5 came from, you could do that. And then I would do the same thing on the bottom. Make sure though, because the amount is a quantity, I'm going to write it this way, 0.35 times in parentheses x plus 15. If you wanted to distribute it right away, you could do that too. And where to go from here, this last column is the column that you use to set up an equation to solve for x. And what it is, it's juice 1 added to juice 2 should equal the mixture or the fruit punch in this case. So the amount of juice in juice 1 is 0.65x plus the amount of juice in juice 2 is 1.5, and that should equal the amount of juice in the mixture, which is 0.35 times the quantity x plus 15. And I now have an equation set up that I can solve. And like I said, I'm setting this up not as a rational equation. I find this is an easier way to set it up. I would just solve this for x, and that would actually give me my answer of how much 65% fruit juice solution we should have. So I'm going to distribute on the right side. So I still have 0.65x plus 1.5 equals 0.35x plus 0.35 times 15, 5.25. And then I'll subtract the 0.35x. And that would give me 0.3x or 0.30x. Plus 1.5 equals 5.25. Then subtract 1.5 from each side. So 0.30x equals 3.75. Divide by 0.3. So x would equal 12.5. And then what would the units be on x? 12.5 what? Milliliters, yep. So in order to get the percent fruit juice they want for the fruit punch, they would have to add 12.5 milliliters of the 65% fruit juice to the 15 milliliters of the 10% fruit juice to get the right mixture. Okay, so yes, these problems are a bit of a process. So what I'd like you to do, if you have questions on this when I'm walking around, you can certainly ask. I want you to work through example 2. It's another mixture problem. So work through setting it up, setting up your equation, finding an answer. If you get stuck, I'll be walking around. I'm going to give you a minute to try something first, but I'll be walking around. So if you get stuck, let me know. As I walk around, I can check your answers too as I walk around. All right, so I know some of you might still be finishing up. Some of you had the answer, so I was able to check it right away. It should be 21.3 or 0.33 or 0.3 repeating, which is 1/3. So if you had 21 and 1/3. And I know some of you, there's might be some confusion, and that is absolutely fine right now if how to set this up is a little confusing. That is why I stress the practice. Because if this is the first one you're working through, yes, you might feel confused. The only way to get less confused about it is to practice it and continue asking questions like some of you were doing, which is great. Yes, Cora? Multiplying x by 0.0 or 0.8. So these two across are always multiplied because you're taking the amount of the solution and the percent of the brine to get the amount of the brine. So these are multiplied across. Okay, any other questions on example 2? And there will be on the assignment, there are a couple that are just practice with mixture problems. Okay, then the next example I have for you is not a mixture problem, it's a work problem. Showing you how to work with these. And this one will be set up as a rational equation like we saw yesterday, so where you have to find a least common denominator. So if you look at example 3, it says it took Anthony and Travis 6 hours to rake the leaves together last year. The previous year it took Travis 10 hours to do it alone. How long will it take Anthony if he rakes them by himself this year? Okay, so how to kind of think through this one and set it up. It's talking about them working through a specific task, raking leaves. So if it took Anthony and Travis together 6 hours to rake the leaves, this is how you set up the rate. So if I say, I'm just going to put A plus T for Anthony and Travis together. So their rate would be 1/6, and I'll explain why. So if it takes them 6 hours to rake the leaves together, what this 1/6 means, it means in 1 hour they were able to rake 1/6 of all of the leaves. So you could even say it's 1/6 of the leaves per hour. So whatever amount of time it takes somebody, it's always going to be 1 over that, because it's representing if it takes them 6 hours to rake all of the leaves, they can rake 1/6 of the leaves per hour. Okay, so that's Anthony and Travis together. Then it says the previous year it took Travis 10 hours to do it alone. So just Travis's rate would be 1/10. If it's 10 hours to rake the leaves alone, he can rake 1/10 of the leaves per hour. And then the question is, how long will it take Anthony if he rakes them by himself this year? So Anthony's rate, we don't know how long it takes him. So I'm going to say his rate is 1 over x. We don't know the amount of time it actually takes Anthony to do or to rake the leaves by himself. Okay, so then here's how you set up an equation. And it should be kind of intuitive. So we have their rate together, and then we have the rates of each of them separate. So what we're going to do is we're going to take Anthony's rate of 1 over x plus Travis's rate of 1/10 should equal the rate it takes them together, which is 1/6. So Anthony's rate alone plus Travis's rate alone should equal their rate together. Okay, so that's our rational equation. This is now an equation like we learned to solve yesterday. So from here you need to find what the least common denominator would be so that you can multiply everything by the least common denominator. So for x, 10, and 6, what's the least common denominator? $30x, yes. And actually, even if it's not the least common, like if you said, okay, well, 60, you could also use 60x. It's still going to work. So we usually try to find the lowest denominator, but any common denominator would work. So I'm going to multiply everything by 30x over 1. This is like what we did yesterday. And then I should see that all of my denominators cross out. I can cross simplify. So that first fraction, I can cancel out the x's, and I'm left with 1 times 30, which is just 30. Plus the second fraction, I can cross simplify the 10 and the 30. So the 10 just becomes a 1, the 30 becomes a 3, and I'm left with 1 times 3x on the top, so that's just 3x, equals the last fraction. I can cross simplify the 6 and the 30. 6 becomes a 1, 30 becomes a 5, so I'm left with 1 times 5x, so just 5x, and then I solve for x. So I can subtract 3x from both sides. So 30 is equal to 2x, and divide by 2, meaning x is 15. So it would take Anthony 15 hours if he was raking the leaves by himself. Okay, questions on that one? All right, so example 4 is another work problem. So work through example 4. I'll give you a little bit of time here before I start walking around, but I can walk around, check what you have, answer questions. I'll also pass out the assignment. There's 4 questions on the assignment, 2 are mixture, 2 are work problems for extra practice. All right, when you're ready, if you're not quite done, you can look up here to check your answer if you're still working on it. I put multiple ways you could express the answer. Some of you had the answer already when I walked around and you were fine. So, like I said, the assignment has 2 mixture problems and 2 work problems. For the first problem, it is a mixture problem. It's a little different because rather than having percents, you have dollar amounts. So for number 1, treat the dollar amounts like you treated the percents in the examples that we worked through. But you have time to work through these right now, so work through it. Let me know if you have questions.